We're doing part 3, formula determination. So we talked about moles and molecules and atoms. So we're going to take it farther into the molecule. Okay, the first thing you can do is if you have a known formula, you can do the determination of the formula by amount, or if you know the formula, you can get the percentage, or you can actually work it backwards, and I'll show you how we're going to do that. So we have C12H22O12, which is sucrose. And if you'll notice, if we find the total mass, and we have each component, this is carbon, this is hydrogen, and this is oxygen, then we can do the percentage of each one. So the interesting thing is when you look at this, you'll say, oh look, I have 22 hydrogens. So most of my molecule is hydrogen. Yes, by atom, but by mass, if you'll notice, is only 6%. So it's a function of whether you're looking at the numbers or whether you're looking at the mass amounts. Okay, so for some reason I had a slide in here. It's gone now. I'm not sure where it went, but I want to go ahead and work it. And what this is calculate the molecular weight of heptanoic acid. And heptanoic acid has this formula here. So if you look at it, we have 7 hydrogens. We have oxygen. We have 2 of those. In the hydrogens, we have 14. So if we go look up the atomic weights, this is gram per mole. These are all going to be gram per mole times 15.9994. And this one by 1.008. Then if we total this whole thing, we get 130.1878, and that is the molecular weight of this compound. Now, if you've noticed, I used 15.9994. Why did I use that? Well, that's the accurate mass, atomic mass of oxygen on the periodic table I'm using. So your numbers are a function of your periodic table. You've taken the first test, so you'll know that significant figures are kind of a function of what numbers you use, so you can see that as you go. Now, on the second one, calculate the formula mass, and it's called a formula mass because this is a salt. We know it's a salt because it's got ionic compounds and it's got a metal. And so this one we would need the formula. So it's cobalt and sulfate. Cobalt is 3 plus, sulfate is 2 minus. So that would be the formula, which means we have 2 of those, 3 sulfurs, and 12 oxygens. Again, if we look at our mass, our cobalt is 58.9332. And again, this is in grams per moles. The sulfur is 32.066. And the oxygen is 15.9994 again. So when we're done, we end up with a formula mass of 406.0572 grams per mole. Now, formula mass, molecular mass, what's the difference? Well, technically, formula mass is the weight of salts. Molecular mass is the weight of molecules. And molecules are composed of non-metals, whereas salts are composed of ions, metals plus a non-metal, etc. In this book, text especially, and as we go through stuff, we're going to look at things and we're going to use molecular weight and formula weight interchangeably. Is that correct? Technically, no, but we're going to tend to do it anyway. Now, this particular slide may be in the stripped out slides to fill in. It may not be. If it's not, I apologize. I'm not sure where it got lost because I was expecting it here and it disappeared, but there are several of these in the back of the chapter, so you can do those as you go. Now, that brings us to what are we talking about in terms of empirical formulas and molecular formulas. Remember, an empirical formula is the smallest whole number ratio. Between atoms in a compound. Okay, the molecular formula is the actual whole number ratio between atoms in a molecule. Now, the interesting thing is that molecules tend to have, not always, have formulas that are large. Empirical formulas are the smallest ratio, and that is also what you have with salts, is just empirical formulas. So basically, a molecular formula is an empirical formula multiple. So if that's your empirical formula where you have 2 carbons to 4 hydrogens to 1 oxygen, then if you multiply it by 1, you get this species. 2, 3, 4, ongoing, repeating. Now, why would you want to do that? Well, it's actually what happens with molecules in nature, organic type molecules. And so the effect is if they have the same empirical formula, they tend to have similar properties. So sometimes you'll classify compounds based upon their empirical formulas because those tend to have, in organic, you'll get functional groups, etc. Like talk about sugars in biology and things like that. So that's why it's important to be able to differentiate. Now, how do you determine the formula of a compound from the percentages? Okay, well, there are a couple ways to do this. First one is the most straightforward. That's mass percent. That is strictly you take the percentage of the species present, and by species I mean the elements. That's the most straightforward way. The second way is elemental analysis. Now, elemental analysis is actually the most commonly used if you're dealing with organic molecules, because what you do is you convert all the carbon to CO2 and all the hydrogen to H2O because you're adding extra oxygen. What you're really doing is burning things up. And organic compounds, things that contain carbon, tend to burn well. Things that don't contain carbon don't always burn well. But in this elemental analysis, you're going to burn it. And here this one catches the, water. And this one catches the CO2. Now, the trick to remember on elemental analysis, it's really critical, is that you cannot count oxygen because you keep pumping it in. Okay, so let me show you how to do this. If you follow these steps and you go down them, never go backwards, then you'll be good to go. And this starts with both, so you're going to start with the amount of each element. Now, it can be in the form of compound or not, that varies. Okay, we're going to convert the amount to grams of the element. Now, if it's mass percent, you assume 100 grams and convert directly to grams. So what that means is if you're told that you have 12.4% carbon, then you assume 100 grams, so that becomes 12.4 grams of carbon in the compound. Okay, that's the easiest way. If you have grams of a compound, then you're going to convert it to grams of an element. So, for example, if you do a combustion analysis and you're given CO2, then you have to figure out the grams of carbon in the CO2. And you're going to do the hydrogen in the water. Now, be careful because reading is fundamental and we all forget to read. I'm kind of the queen of that. But there's a 2 there. So in water, you have 2 hydrogens. In carbon dioxide, you only have 1 carbon. Now, once you've got the grams of whatever element you have, you're going to convert it to moles. You use the atomic weights here. Then, only then, you're going to compare the mole-to-mole ratios. You divide by the smallest one. And then you're going to reduce the whole number integers. And this is where it gets a little strange because you're like, rounding rules? No. You may round 0.1 and 0.9. You may not round 0.2, 0.3, 0.4, 0.5 through to 0.8. So if you would have 1.3, you would multiply it by 3 so that you could have 3.9. Again, you can round that. Okay, this one would be 5.0, so obviously it can be rounded. At this point in time, you have the lowest whole number ratio. This is the empirical formula ratio. I keep trying to put an N on there. Okay, so for ionic compounds, the empirical formula is the formula for ionic compounds. For molecules, it begs the question, does the empirical formula equal the molecular formula? There are a couple ways to do this. The common way is there a molecular weight given? So if the molecular weight equals the empirical weight, then they're the same. If the molecular weight is equal to a multiple of the empirical weight, then you distribute it. So if your empirical weight, and I'm making up numbers, is 22, and your formula, your molecular weight is equal to 90, then if you multiply this by 4, that gives you 88, which is approximately 90. So the empirical formula times 4 would give you the molecular formula for that example. Okay, that's not always true, but there you go. So that's the first way. The other way to do it is to include the number of atoms. So for example, if my empirical formula came out to be C1H3Cl, and I was told that the compound has 3 carbons, then that means the molecular formula would be equal to C3H9Cl3. Whoops, 3 chlorines. If I do 3 chlorines, you get that. If you did 3 carbons, actually we get the same thing. So, if there is no information given, assume that they are the same. And I know, and you know what happens when you assume things, and that's okay. Because we're going to work some problems and I'm going to show you how it works. Okay? So, some hints: always proceed forward down the process, never go backwards. Don't round until the very end. And this is actually critical because if you round too soon and you have really small numbers, then you tend to throw yourself out of whack and you get... It usually affects weird rounding first, but okay. Now the other thing is all percentages must add up to 100. So if you're given 3 compounds and the first one is 40% and the second one is 30%, then that's 70, so the third one has to be 30%. Okay, don't randomly make up numbers. Okay, if you have grams, then they have the total. Be careful to use atomic weights, not molecular weights. You want to use 15.9993, approximately 16, not 32. Okay, and distribute the empirical to molecular formula, just don't leave it out front. Okay, so having said that, let's work our first one. Okay, we're told that a sample contains percentages of chlorine, carbon, and hydrogen. Okay. Molecular compound is known to have 2 chlorines. What are the empirical formulas? Now, you can work this left to right or top to bottom. I like to work left to right. I'm just kind of a left to right kind of girl. And the reason why I say that is if you keep things in order, then you don't have to keep up with your units so bad because your units follow. And it is critical in chemistry 1211 that you keep up with your units. So we're going to do chlorine in this row. We're going to do carbon, and we're going to do hydrogen. We don't have to do them in that order, but that's the order they're given in, so it's easier. We're going to start by assuming the percentages are grams. So 24.27 grams and 4.07 grams. Now, I would put in the atomic weights, etc., and I'd have to keep spelling out chlorine, etc. But since I'm going to do it left to right, I know everything I do in this row is chlorine. So if I look at the periodic table, 35.4521 grams per 1 mole is equal to 2.02100. Now, this is the mole column. This is 12.0107 grams. You could use 12.011, just don't use 12, okay? That's too much, or too little significant figures. 2.020698 and 1.00794 grams per 1 mole. So we have a whopping 4.0379387 moles. Now at this point in time, we're going to divide by the smallest, which in this case, when you have two that are really close, it really doesn't matter, but the smallest happens to be 20207. So what that ends up with is 0.9947, 1, and 1.998. So we have a 9 here. We actually kind of don't look at the number behind it. That's 1. This is 1, and this is 2. So we've reached our whole number ratio. That means our empirical formula is equal to 1 carbon, 1 chlorine, and 2 hydrogens. Now, does it matter what order you put them in? No. You could put H2CCl. You could do CCH2Cl, whichever one floats your boat. Okay, and then you're told that the molecule has 2 chlorines. That means that you need 2 times the empirical formula, which means your molecular formula is going to be C2Cl2H4. So you're given the information there, and you have something to work with. Okay? So that wasn't too bad. So because that one wasn't too bad, let's go ahead and work the next one, which is a combustion analysis problem. We're going to work 2 that are combustion and 2 that are not. So on this one, we have carbon, hydrogen, and oxygen. We're given water and CO2, which is generated. What is the molecular formula of the compound? So in this case, these are a little bit harder, but again, we're composed of carbon, hydrogen, and oxygen, and I'm going to start with hydrogen. Does it matter? No. I just happen to have started with hydrogen here. So the first thing we want to do is calculate the grams. That's the first point. Now, so for the hydrogen, we know that we're given 0.0928 grams of water. And we know that for 18.016 grams of water, we get 2.016 grams of hydrogen, which gives us a whopping 0.0104 grams of hydrogen. Now, at some point, somebody could have said, wait, why didn't we just go to moles? Yeah, we could have gone to moles. The problem is that we know we're composed of carbon, hydrogen, and oxygen, and we're given a mass. We're going to be able to calculate the grams of carbon and the grams of hydrogen. We're going to get the grams of oxygen by subtraction. So let's continue on. 0.288 grams of CO2. And again, we had 2 hydrogens for every water. We only have 1 oxygen, 0.088 grams of CO2 per 12.01 grams of carbon. That gives us a whopping 0.0786 grams. Okay, again, we're carrying through. Now, the grams of oxygen comes from the total grams minus the grams of carbon minus the grams of hydrogen. So our total grams are 0.1000 minus our grams of carbon, which is 0.0786, minus 0.0104. So that gives us a whopping 0.0110 grams of oxygen. Now, we're going to divide by the smallest. Nope, not yet. We have to be to moles first. So let's get them to moles. So 1.008 grams per 1 mole is 0.01, whoops, 03, 12.011 grams per 1 mole is equal to 0.006544. This is 15.9994 grams per 1 mole. So that would be a whopping 6.875 times 10 to the minus 4th moles. Now, at this point, you're like, wait, these are really small numbers. Yeah, they are, and that's fine. But we are at moles. We're at the mole stage. So now we can divide. So we're going to divide by the smallest, which in this case, if you look at it, it's going to be the oxygen, which is 6.875 times 10 to the minus 4th. Do you have to write in scientific notation? No, not if it doesn't make you happy. Okay? So once we do that, we're going to get 14.98. We're going to get 9.5185. And we're going to get 1. So that means that at this point in time, we have 15 hydrogens. We have 9.5. Remember, we can't round 0.5, so we have 9.5 carbons. We have 1 oxygen. So we look at the decimal, which is 0.5. So what do you multiply to get 0.19 or 0 times 2? So we end up with hydrogen is 30, carbon is 19, and oxygen is 2. So these are the lowest number ratios. So our empirical formula is equal to H30, C19, O2. And now it doesn't matter whether you start with carbon, hydrogen, or oxygen. That doesn't matter. Now the question is this is actually a pretty big empirical formula. Is it just the empirical formula? Well, let's go look. What is the molecular formula for the compound? We're not giving you any of the information. So we're going to assume that this is also the molecular formula. Do you have to rewrite it? Nope. As long as you identify it there. If you are asked to fill in the blank on like D2L and you're asked for the empirical formula and you're asked for the molecular formula and they're the same thing, then because the electronics are not forgiving, then you're going to have to rewrite it twice. If I was hand grading it on a test, then this form would be fine. Okay, so far so good. We've worked one that is a combustion analysis and one that's a percentage. So let's go back and look at the percentage again. We have the action of bacterial meat produces a poisonous compound cadaverine. This is actually a real compound. I happened to read this and I thought, this is appropriately icky. So we're going to stick with it. So we're given percentages here, and we're given the molar mass. Now, some people like to start with the molar mass and work backwards. I don't recommend that because when it says between 102 and 103, it could be 102.1 or 102.99. Bottom line is we don't know where it is, and it doesn't seem like 1 AMU is a big deal. It can be. So you need to be very careful. So we're going to work carbon, hydrogen, and nitrogen. So the carbon is 58.77%, which means that's how many grams it has. So, as I said, you can set them up and wait to work them, or you can do what I'm doing, whatever floats your boat. But you can't go any farther than the moles, because that's what you've got a ratio. Hydrogen is 13.81 grams, 1.00794 grams. So it comes out to be a whopping 13.70121. And 27.42 grams of nitrogen, and nitrogen is 14.00674 grams per 1 mole, which gives us a whopping 1.95763. So we're going to divide by the smallest, which in this case is the nitrogen, which is 1.95763, which means this one's 1. This one comes out to be 6.999, and this one comes out to be 2.4995. So when we round it, this goes to 2.5, this goes to 7, and this goes to 1. Now, 2.49, you're like, wait, you can't round 4. No, you can round it to a 5, but you can't round the 5 from there. So because it's a 5 again, we're going to multiply it by 2. So we're going to get 5, 14, and 2. So C5H14 N2 is your empirical formula. Now, it's told that our molecular weight is between 102 and 103. So if we take and we approximate this as our empirical weight, 5 times 12 is 60, plus 14 is 74, plus another 24, 74, 94. So that's approximately 102. Again, I don't have to have exact values here. I'm just approximately. So the empirical weight is 102. That's pretty much equal to the molecular weight. So that means my empirical formula is equal to my molecular formula is equal to C5H14 N2. So again, in this particular case, both answers will work. Okay, because we enjoyed that so much. Oh, and by the way, you're going to have one of these full on the test and the other small pieces parts. So just be aware that you will need to know both. Okay, we'll do another one that involves combustion analysis. Of the two problems, more people have a problem with the combustion analysis because it's got extra steps to it. So we have a compound contains carbon, hydrogen, and oxygen. And also pay attention on a test or in other problems because it may contain nitrogen. Well, if it contains nitrogen, it works identically the same way. You just don't have oxygen. So be careful for what it has. So we've got the CO2 and the water. And wait a minute, all these units are in milligrams. Ooh, so you're going to need to be careful. So we'll start with our carbon, our hydrogen, and our oxygen. So we have 0.01601 grams of CO2. And we know that it's 44.008 grams per 12.011 grams. And that gives us a whopping 0.0043697 grams. Okay, for the water we have 0.00437 grams of water. 18.016 grams of water per 2.016 grams of hydrogen. And I was really zealous with that line. That gives us 0.004, zero. 3 zeros. Let me erase that and clean it up here for you. 0.123489005 grams. And then oxygen, remember, is the total minus the grams of carbon minus the grams of hydrogen. So in this case, we have 0.01068 minus 0.0043695, 7 minus 0.000489005. That's a grams. Okay, which means that with the oxygen we get a whopping 0.0058214 grams. Wow. Okay, so let's go back up here, and we've got 12.01 grams per 1 mole. So we have 3.63797 times 10 to the minus 4th. Remember I told you some of these might be really small, and that's a function of what you're working with. So we got here 4.8512 times 10 to the minus 4th. And again, these are all the moles. And my hand is starting to cramp. 0.59994 grams for 1 mole gives us a whopping 3.6385 times 10 to the minus 4th. Now, once we've got to moles, we may divide. We cannot divide until we get to moles. If you divide at grams, you get wrong answers. So we're going to divide by the smallest, which in this case, wow, they're all -4. So let's look for the smallest one. That will be 3.63797 times 10 to the minus 4th. And again, you don't have to write smallest. You can just write the number, or you can write smallest as long as you follow it through. So that's going to give you a value of 1, 1.33, and 1.08. So that means we have carbon equal to 1, hydrogen equal to 1.33, and oxygen equal to 1.08. Now, if I was working on this on paper and I still had room, I'd keep going to the right. Now, I cannot round, okay? No rounding, because you cannot round a 3. So we're going to multiply by the nearest number. Well, what number multiplied by 3 will give you a 1 or a 9? And you're like, 7. Okay, yeah, that too, but 3. 3 would be the smallest. So we get 1, we get 3.99, and we get 3. So then again, whole numbers, 1, 4, and 3. So my empirical formula is C1H4O3. No, I can't multiply. Did y'all let me get away with that? Okay. 3 times 1 is 3. This is what you call typos. Okay, so that's our empirical formula. Now, are we given more information? We're told that the empirical molecular weight is equal to 176.1 grams per mole. So if we do our mass, our empirical weight here is about 88. So if you multiply that by 2, you're going to get approximately 176. So 2 times the empirical weight gives you the molecular weight. So 2 times the empirical formula will give you the molecular formula. So that means that the molecular formula is going to be equal to C6H8O6. Okay, so at this point in time, this is how you do combustion and percent analysis to determine empirical and molecular formulas. And again, expect both of these in some format on the exam. You know, you may not be asked to do the whole thing. You may only be asked to do pieces, parts, and that's fine. But the bottom line is, remember, never go backwards. So if I happen to give it to you on the exam and I give it to you in the moles, then it's just straightforward ratio and move on. Don't go back to grams. That's the hardest part for some people, is don't go backwards. Okay?